Hello viewers, my name is Geoffrey Omondi. Welcome once again to our class of probability. The last time we were in this class, we were able to discuss about combined events that occur at the same time. And the first case we looked at that situation was mutually exclusive events. So this is probability. And in probability, we were able to look at occurrence, the probability of occurrence of combined events. So this was the last class. And we said that combined events, there are two types of combined events. You can look at probability. Of mutually exclusive events. Still, you can look at probability of independent events. Dependent events. So as we are saying, that was in the last class. So we looked at probability of mutually exclusive events, but independent events we didn't look at. So we are going to look at this in our today's class, or what we are now calling this class. Now, we agreed that mutually exclusive events are those events that when one occurs, the other one cannot occur. For instance, we say that when you throw a coin, you cannot have a head and a tail at the same time. You can only have a head or you can have a tail. So that kind of event is called mutually exclusive events. But today I want us to look at independent events, where we can just write it, independent events. Now, this kind of event, occurrence of one event does not depend on the other. So we are looking at probability of occurrence of events where occurrence of one event does not influence occurrence of the other. So that is the scenario we are looking at. Probability where occurrence of one event does not influence occurrence of the other. Now, we can give a number of examples. For instance, so let's give a scenario or a case. Let's give a case. If you toss a coin, and at the same time cast a die, then consider the probability, the probability of getting a head for a coin and 3 for a die. Now, when you toss a coin and cast a die, the events of the coin are independent of what you will get where you've cast a die. In other words, you can get either head or a coin, or either a head or a tail for the coin, and for the die you can get any number, and what you get for a coin does not actually depend on what you get from the die. Each can happen on its own. Such events are called independent events. Such events are what we are calling independent events. Now, let me just write this to the side. Now, For instance, we can say this is the probability that you'll get a head and the probability that you'll get a 3 for a die. Now, when you're dealing with probability, and here is very, very important. And is very important. And normally, and mathematical symbol for it can be written as times, such that you can now say this is the probability of a head times the probability of getting a 3 in the case where you did cast a die. I am again saying this is very important. That is very important. You have to remember it. Now, in this instance, therefore, the probability of getting a head in this case is a half. Now, by now, I know why you should be aware why we are saying it is a half. It is a half because there are only 2 chances in the sample space of tossing a coin. That is either you are getting a tail or you are getting a head. So those are 2 chances, and our favorable outcome, which is a head, is only 1. So it is 1 out of 2 times our chance of getting a 3. Now, when you cast a die, there are 6 possible outcomes. You can get a 1, a 2, a 3, a 4, a 5, or a 6. So a 3 is just 1 out of the total 6 chances. So we can multiply this and say that our answer is now 1 out of 12, which is actually the probability of, when you toss a coin and cast a die, this is the probability of either getting is the probability of getting a head on the coin and getting a 3 on the die. I want us to look at other examples so that we can see what is happening. Now, viewers, I want you to be very keen, and I want you to know that this is what we are calling the multiplication law of probability. Multiplication law of probability. This is the multiplication law of probability. Now, I want you to be keen and note that what we have here, we can also do it in another way without looking at the multiplication law of probability. For instance, we can draw and say that we have a coin. Now, when you are dealing with a coin, it's either a head or a tail, that it is sample space. At the same time, we are having a die. A die will give you can get a 1, a 2, a 3, a 4, a 5, or a 6, like that. So that one will be that. You can also do that. And this, you can do that like that. So from here, you can clear very well. Come and clean here like that. And can do that like that. Now, from this, it means that you can get 1 for the die and a head, or you can get 2 and a head, or you can get 3 and a head, or you can get 4 and a head, or a 5 and a head, or a 6 and a head. Still, you can get 1 and a tail, 2 and a tail, and a tail, 4 and a tail, 5 and a tail, 6 and a tail. Now, looking at this, therefore, we can still find the probability of getting a head and a 3. So, looking at all this, our head and 3 falls here. Let me surround it with the red ink. That is our head and 3. And you realize that our head and 3 is only 1 outcome. But what are the total number of outcomes that we can have? It is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So, favorable outcome we are looking of over the total number of outcomes 12. That is the probability of getting 3 and a head. So you can notice very clearly, we can still get the same answer here without using what we call the multiplication law of probability. So we have used two different ways to solve that. We can look at another example. We can look at another example very fast. And look at another example. Can look at another example. A coin is tossed twice. A coin is tossed twice. What is the probability? What is the probability? Is the probability of getting a tail in both cases? Getting a tail in both cases. A tail in both cases. What is the probability of getting a tail in both cases? Now, looking at this, we know that if a coin is tossed twice, your first outcome, be it a head or a tail, does not influence your second outcome. You can get a tail in the first one and get maybe a head in the second one. So the best thing that we can do is to say that to get, so we'll work with first toss, and then second toss. So we are saying that we want a tail in both cases. So we want the probability of a tail in the first case and probability of a tail in the second case. Now, working with this, in the first toss, probability of a tail is actually a half because it is 1 out of 2 outcomes, head or tail. And we have said this multiplication law, it is times. Probability of a tail in the second is also a half, giving us 1 times 1, 1, 2 times 2, 4. So that gives us a probability of what we call a quarter. This gives us probability of a quarter. But I want us to agree that you can also draw a sample space and get that without using what we call the multiplication law. So let's draw a sample space for that and see what happens. Let's draw a sample space and see what happens. So we can say that we have two coins. We have coin 1. And in coin 1, we have a head and a tail. We can also say we have coin 2. And in coin 2, like that, we also have a head and a tail. So we can do that and do that and do that like this. This is coin 2. Coin 2. Now, working with that, this is now our sample space. So the possible outcomes here would be head, 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 tail, tail, head, and tail, tail. So from here we can easily see that tail, tail is only one outcome over the total outcomes is 1, 2, 3, 4 over 4. So you see that we can also find this answer by simply drawing a sample space and using it to find, instead of using our multiplication law. I want us to look at another example so that we have enough practice. I want us to look at another example to give us more practice. So a boy, another example, a boy throws a fair coin. A fair coin, it means this is a coin without any defect. The chance of getting a head or a tail is similar. So throws a fair coin coin, and a regular tetrahedron, and a regular tetrahedron. With its faces, with its faces marked 1, 2, 3, and 4. Find the probability. Find the probability. Find the probability. So find the probability that he gets a 3. That he gets a 3. That he gets a 3 on the tetrahedron. On the tetrahedron. Tetrahedron. And a head on the coin. And a head on the coin. So again, this is possible to work out using two formula. We can use the formula of multiplication law, or we can also draw a sample space and count from the sample space. So in this case, let's look at solution. Let's look at solution. Solution. Now, the probability here, we can say this is the probability of getting a head and the probability of getting a 3. Probability of getting a 3. So the probability of getting a head when you toss a coin, a fair coin, is normally 1 out of the possible 2 chances. So that is a half, and means times. Probability of getting a 3, we have 1, 2, 3, 4. So we have 4 total chances. So getting one of them, which is 3, is actually 1 out of 4. 1, which is 1 chance. 3 is only 1 out of a total of 4 items. So it is 1 out of 3. So when you multiply this, you simply end up with 1 out of 8. But this is one way of doing it. It's correct. We'll mark you that way. You can also get this by drawing what we call a sample space. You can also draw a sample space. You can also draw a sample space. Now, in our sample space, we have a coin. Coin. And our coin is a head and a tail. At the same time, we have tetrahedron. 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 So our tetrahedron is marked 1, 2, 3, and 4. So we can do this, can do that. So from there, we can work it out and find that we can either have 1 on the tetrahedron and a head, 2 on the tetrahedron and a head, 3 on the tetrahedron and a head, 4 on the tetrahedron and a head. Still, get 1 on the tetrahedron and a tail, 2 on the tetrahedron and a tail, 3 on the tetrahedron and a tail, and 4 on the tetrahedron and a tail, like that. So from this, these are our outcomes. Those are our outcomes. So we can now work, and the question wanted us to get a 3 and a head, which is here. This is a 3 and a head. So working with this, we'll now say that a 3 and a head, when we look around, is only 1 out of, what is our total number of chances? 1, 2, 3, 4, 5, 6, 7, 8 out of 8. So that becomes the probability of getting a 3 and a head. So we are clearly able to see that we can do it by drawing our sample space, and at the same time we can use what we call the multiplication law of probability and still get the same results let us look at another example again. We can look at a further example. The example is three different machines in so three different machines have probabilities of breaking as shown below. So you can take machine, then probability of breaking down. So machine A, the probability is 4 out of 15. Machine B, the probability is 3 out of 10. 3 out of 10. Machine C, the probability is 2 out of 11. So from there, the question still continues. Find the probability A, the probability that all machines will break down. That all machines will break down. Two, find probability that none of the machines will break. Now we can work on that. So we want to start with the first one, solution. The probability that all the machines will break down. Now when you look at that, you'll realize that this means the probability of A breaking down and probability of B breaking down and probability of C breaking down. That is what it means that all machines will break. So we can take the probability of A breaking down, that will be 4 over 15 from here, and multiplication law, 3 out of 10 for B, and multiplication law, 2 out of 11. So in this case, we can continue and say that we can cancel. Let me use a red ink so that you are able to see. 3 can cancel itself once. In 15, 5 times. From there, we can say that 2 can cancel itself once into 10. 2 cancels 5 times. So that would leave us with 4 times 1, which is 4, over 25 times 11. So that will give us 275. That would give us 275. So this will be the probability that all the machines will actually break down. That is the probability that all machines will break down. Now, probability that none will break. This is normally given by, so that was a solution for A. I want us to look at solution for B. The probability that none of the machines will break. So I want you to know this is the same as probability of A not breaking. Now, when we use this I, it means this is not. So when I say A and a small 1 on top, it's like I'm saying A not breaking. And also the probability of B, I use this to say not breaking. And also the probability of C not breaking, like that. Now, when we were introducing probabilities, we say that if you have 1, for example, if the probability of breaking is 4 over 5, 4 over 15, it means the one of not is actually a whole, which is 15 out of 15 minus 4 over 15. Or you can say it is 1 minus 4 over 15 to give you the one of not breaking. So in this case, not breaking would be given by 15 out of 15 minus 4 over 15, giving us 11 out of 15, and is times. B breaking is 3 over 10, so not breaking is 1 minus 3 over 10, which is actually 7 out of 10, times C not breaking, here is 11 over 11 minus 2 over 11, which is actually 9 out of 11, like that. So we can work this one out, and I can use a red ink to show how you'll work on it. This one and 11 and 11 can cancel. 3 can cancel this 3 times and cancel that 5 times. So that what we will now remain with is 7 times 3, giving us 21, over 5 times 10, giving us 50, like that. So again, that would be the probability of A not breaking, B not breaking, and C not breaking, which is actually none. So I want us to continue. Let me clean here. Let me clean here. Now, when you look at this question, it is important that you know that there are a number of questions that you can be asked. Now, for this class, therefore, I want to believe the examples we've done will do you good. We are going to do more examples in the next class. For now, I want to leave you with an assignment. You'll attempt later. That assignment would be exercise 13.3. This is KLB. So I want you to work on numbers 1. So numbers 1. I want you to work on number 2, number 3, number 4, and number 5. Now, in the next class, we are going to do further exercises on independent events. So our next class, actually, before we can introduce the next concept, will still be on independent events. So we are going to do further exercises combining independent events and mutually exclusive events. Otherwise, for this class, I want to say let us stop there for now and have a nice time. Bye. I was your host, Geoffrey Omondi.